information versus imperfect information. What's the difference in terms of your game? Now, your game you can write in decision tree. So decision tree means extensive form. Or you can write the game in normal form. Normal form means matrix. Right. Now, which form should you write? The table or the tree? If you write your game in the table or tree, the answer depends on what method you use to solve. Now, if the question asks you to find the pure strategy net superable or mixed strategy net superable, what do you draw? You draw a tree or a table. You cannot find a pure strategy net superable from a tree. You have to draw the table. Simple. Draw a mixed strategy net superable. Draw a tree or table. Draw a table. Now, of course, if the exam question asks you to find this thing, draw a tree or draw a table. You must draw a tree to solve this. Okay? First one, elimination. Elimination, you use tree or table. Okay, for sure table. Okay, so that's why before you start doing the question, the first thing, you identify the problem. Now, you know there are two types of game, perfect and imperfect information. Now, in the case of imperfect information game, if I ask you to find the pure strategy net superable, so what must you draw? You draw a paper, right? Now, but most of the time, the exam question, they may not give you the table. So if they don't give you the table, then you must know how to fill up the table yourself. Right? Because to find pure strategy, you have to create this. Now, when there's imperfect information, player one has how many strategy? Either play this or play this, right? So pick R or pick R. Now, player two has how many strategy? Now, in an imperfect information game, can the players see each other? Cannot. Right? That's why imperfect information. Now, if I cannot see what you do, you cannot see what I do. That's the reason why we have imperfect information. Okay? If I can see what you do, you can see what I do, then it's both of us have perfect information. So therefore, if there's no perfect information, every player cannot see what each other do. And the very best player too can be what? Either play this or play this. Cannot make any plan. And so that's why you can see the strategies available to do is either to play this or play this. Only two strategies. Now, whereas I said before, for the case of perfect information, then the story is different, right? Why? How can people have perfect information? Every second, I can see what you do, right? That being the case, the story is slightly different. Because the player can see each other. Then in this case, the game will become something like this. Player one has found strategy, either this or this. Now, how come player two got so many strategy? You Because player 2 can see what player 1 does. And so therefore he can say to himself, because he has perfect information. So he can do this. If he saw player 1 play this, player 2 can plan to play this. But if he saw player 1 play this, he can still plan to play small r. Right, therefore, RR is one set of plan. Good? So what's the meaning of RR? RR means what? Here play R, top play R, below play R. Okay? Now, are there any other plan that player 2 can formulate? Now, since you can see what player 1 does, another set of plan will be, if you saw player 1 play this, you can plan to play small I. If you saw player 1 play big I, you can say to himself, I can still plan to play small I. So II is one set of plan. Okay? So we have found so far 2 plans. Now, how come you can make so many plans? You can only make so many plans if you can see what the result are right. If you cannot see, no plan. Either play small r or small I. Is it? Just like before. Now here, because you can see, that's why you can create so many plans. Now, we can keep on looking at the tree and create some more plans, but it's a waste of time. So the trick is very simple. I find this same, right? From there, I just have to think of the combination we do instead of every day looking. Now, what other combination can we have beside here? RR, RI. Any more? No more. Now, what other combination can we have beside this one? IR. Any more? No more. Okay. So therefore, there are 4 sets of plans. So player 2 has 4 strategies. Easy? Okay. So once you fill up the strategies, you have to fill up the payoff. Now the payoff for this case is slightly different. Slightly different because, for example, we have to ask you, this is the payoff for what strategy? What strategy? Okay, player 1 play what? Player 1 play big R, player 2 small I or small r. Okay, player 1 is the role player in strategies. Either strategy this or this, right? It's a role player. Column player, the strategy is either this. So we said before, player 1 play big R, player 2 play what? Small I or small r. This row 1 should be matched with what? Column 1, row 2, column 2, row 3, column 3, right? Okay, so very simple. This is column 1, column 2. This one? Column 1, column 2. This one? Column 1, column 2. Okay, so very simple. Row 1, column 1 or column 2? Column 1. So big R, small I. Big R, small I, here. Okay? Big R, small I. This is the payoff for what strategy? Player 2 play, no, player 1 play what? Big L, player 2 play what? Player 2 play small r, small I. This is row 1 and row 2. Row 2, so row 2 should be matched with column 1 or column 2? Column 2. So big L, small I. Big L, small r, small 2. Simple. Okay, after you fill out your table, now you have to find the pure strategy Nash variable. Very simple. How to find? find the pure strategy Nash equilibrium. I think I've done some for you before. For example, and the pure strategy Nash equilibrium medium. Now, if you can recall, pure strategy Nash equilibrium is simply what? A pair of strategies whereby no player wants to change strategy. Right. Now here, can in be the pure strategy Nash equilibrium? Possible. Why? Because the role player, do you think he wants to change strategy from in to out? The role player can move up and down, right? Do you think he wants to go from 8 to 5? No. Then can the equilibrium be here? Why not? The column player wants to move from 1 to 1. Change strategy from in here to here. So his payoff can rise from 1 to 10. Column player wants to move right, out. So if someone the player wants to change strategy, cannot be equilibrium. Because equilibrium in English means final outcome. So in order for this to be the final outcome, both will not want to change strategy. Now, can this be the Nash equilibrium? Out in. Alright, because the role player wants to move from 5 to 8. Now, you know this role player can only move up or down, right? Why? Because the strategy available to him is this up or down. Column player can only move left or right. Cannot move up or down. Because the strategy is available to player 2, column player is this. Okay, so this round will go up. You have to check for both. Even the column player, I think, wants to move, right? But you have to check for both. As long as one wish to change strategy, that's it, out. The 3 want to come down to 4, yes, out. Can this be the equilibrium? Yes, 1. Will the role player 4 wants to go up to 3? No. Will the column player 4 wants to come to here? No. Therefore, this is the point where both players do not want to change strategy. So that's the Nash equilibrium. Okay. If we say both do not want to change, I think you are wrong. Are you sure the role player don't want to change? Look at here. I'm sure you want to change from 4 to 8. Isn't it? Why is it not want to change? We're moving to here. Is better off. Why didn't it change? And if you change, then it cannot be equilibrium. So how come this guy doesn't change? Because he cannot do it this way. I said before, a role player, can he move sideways? How can he move? He can only do up and down all the time. Right? You cannot move sideways. Because if you are moving sideways, you are what you are doing. You are asking, he is asking the wife to do what? Wife, I don't like to be out. I like to be in. Out more fun. In more fun. Can you please do me a favor? Don't play out, play in. So you're asking the other player to change strategy for you so that you can your payoff is higher. Can that be done? And our wife maybe can. The Wuxi game theory we do with firms. Right? Singtel, tell M1, M1. I don't like you to play out. Why? Because you play out, I get 4. But you play in, I get 8. M1, I want you to change strategy from out to in. As if M1 is very interested. You understand or not? So no diagonal movement for both players. Both players either up or down, other player left or right. Any other question? Okay, so first strategy Nash equilibrium is very straightforward. Mixed strategy Nash equilibrium is even easier. Mixed strategy Nash equilibrium, we assign what? Probability to the payoff. Assign probability x to how often player 1 play t, and therefore 1 minus x how often he play t. Assign probability y to how often he play that, probability 1 minus y how often he play that. This I think you have to go back and read. Then you set up the equation. Right. Then d pi over dx then d pi over dy. You find the answer right away. Okay? So I think that you all know what to do. You sure you know? Okay. I'll ask you the question. Find for me the give me the fixed strategy Nash equilibrium. Give me the fixed strategy Nash equilibrium. Okay, very simple. You just assign probability, right? Assign probability x here, probability 1 minus x here. Here, give me the probability. This is 1. Assign probability 1 here, here how much? 1 minus 1. And here? Okay, so this type of questions will come out. So that's why you have to worry. But in 1997, there was one time she misbehaved. She asked a question like this to find the fixed strategy Nash equilibrium. Now, let me tell you something. If ever we ask you to find your fixed strategy Nash equilibrium, when any of them misbehave, there's only one way you can solve it. That this one can never be solved. Because you can only solve it if you reduce it to what? 2 by 2. 2 by 2, right? So in all the exam questions, don't panic. If you see something like this, all you have to do is to reduce it to 2 by 2. How? You eliminate away one of the dominator strategy. You understand? Reduce one of the dominator strategy. Now in this case, are there any dominator strategy? Yes or no? Yes. How we know? Because you can see here, strategy right is dominated by strategy leader. Right now. So we know. That's how I know it's on. Okay, but of course, you know, in the exam, you will see this. But I'm sure you can find. Look at right and middle. If player 2 were to play middle, his payoff is this. If you were to play right, his payoff is this. Do you agree? Do you think player 2 will ever play right? Impossible. The payoff are all lower. Do you agree? So what you do? Simple, right? In this case, given that a dominator strategy is a lousy strategy, nobody will play right. Throw it away. Okay, is it possible to find the answer now? Sure, right. I'll ask you to find the which strategy Nash equilibrium. Same notation. Clear now. 97 was harder because there was, I think, 3 corner 3 rule. But that's a small thing, right? Just get rid of that. Clear? Until here, then you start ending. Okay, any questions? So no problem, then let's move on to perfect equilibrium. Now, we'll show you question number 1.